Welcome back to 205C Part 2 on feeder and branch circuit requirements for a single dwelling. Now that we've gone over selecting our panel board, the next thing we're going to look at is how to select all the proper things for our branch circuits. Remember that a branch circuit is everything from our last overcurrent device, so the overcurrent device inside our panel, all the way up to the end device. Everything that has come before that last overcurrent device doesn't really matter anymore. We want to make sure that we have sized everything from that breaker all the way through our wiring to our final plug selection the proper way. There are a number of different factors that we need to be aware of whenever we are sizing our branch circuits. First of all, we need to know the characteristics of the loads themselves. So what is its ampacity? Is it rated for continuous or non-continuous operation? Is it a cycling load? Are there any other factors to worry about with heat generation, such as is it bundled together with a lot of other conductors? Or is it running through an abnormally warm area? All these things are going to go into our decision-making process to size our wire. When it comes to our overcurrent device, we're going to look at whether or not we need to have 120 volts or 240 volts, which is the difference between a single pole and a double pole breaker. We also need to know what the rated ampacity of the conductor feeding the branch circuit is, because that's how we size our branch circuit overcurrent devices as well. Table 13 is always based on the conductor ampacity and not the load ampacity. The other thing we need to know is what are the AFCI or the GFCI requirements of our circuit. Do we need to have an arc fault circuit interrupter installed inside the panel board, or can we use a receptacle? As well as a ground fault circuit interrupters. Are we going to use a ground fault circuit interrupter breaker, or once again, can we use a receptacle for that purpose? Continuous operation is a factor that affects us quite a bit, because the longer that a circuit runs, the more heat that circuit can generate. And heat affects our resistance of our wire as well. So remember, heat's the enemy. The cooler it is, the better it is for our efficiencies. If we have a load that is rated as non-continuous, then we can simply use the values that we find in table 1, 2, 3, and 4 directly at face value. We then select the overcurrent device according to table 13 and the conductor ampacity. If our loads are rated as continuous, which most of our loads are, we now have to check them to see what the rating of the equipment is. If the breaker that we're attaching it to is rated at 100%, then we can simply go and look at table 2 values. A 100% rated breaker means it's actually rated for what the handle says it is rated for. So on a 20 amp breaker, I can physically pull 20 amps off there. That is a very rare breaker, and you don't typically find those on a lot of installations except for motors. Normally, most of the breakers that you're going to be working with are only rated at 80%. Therefore, we can only load it up to 80% of what its rated value is. So for a 15 amp circuit, we can only load it to 12 amps. A 20 amp circuit can only be loaded to 16 amps. A 30 amp circuit can only be loaded to 24 amps, and so on and so forth. The first thing we need to do is make sure that we have a conductor that's rated properly for the load. If we have a continuous load on an 80% rated breaker, we have to divide the ampacity by 0.8 and then take that value to table 2. This is going to guarantee that we're not going to overheat our conductors. From the value in table 2, we are going to select our overcurrent device from there. So our overcurrent device will be larger than the ampacity of our load. Let's look at an example on how to properly size the conductors for a hot tub. In this case, we have a 5,000 watt hot tub rated at 240 volts. The first thing we're going to do is to find the ampacity. So we'll take our wattage of 5,000 watts, divide it by our voltage of 240 volts, and we end up with an ampacity of 20.833 amps. The next thing we want to do is ask ourselves the question, is this continuous? And of course, the answer is going to be yes. After that, we need to know what kind of breaker we're going to use, and the breaker we're going to use is an 80% rated breaker. Our next step then is to make sure that we are increasing the ampacity by our continuous factor of 0.8. So we take 20.833 and divide it by 0.8 to get the value required for our conductor. So now we come up with an ampacity of 26.042 amps. Our next step is to look at any other heating considerations. So we want to know, is it bundled with other conductors? Is it in an unusually warm area? In this case, we don't have anything else that we need to know for heating. And next, we look at our voltage drop considerations. If our circuit is too far away from the panel, the extra resistance of the wire itself could affect how our circuit runs. So if voltage drop is going to be a consideration, then we need to upsize our wire. In this case, we're not going to worry about it. With all those questions answered, we're now going to table 2. Now we need to know what the termination temperature is going to be. Typically, it's there on the breaker. However, if you don't know or you're unsure, we have to assume worst case scenario. Rule 4006 states that if you don't know what it is and it's less than 100 amps, then we automatically assume a 60-degree termination temperature. So we look in the 60-degree column of table number 2 to find a value that's bigger than 26 amps, and we come up with a number 10 gauge conductor rated at 30 amps. Our last step is to take the conductor ampacity and go to table 13. Table 13 tells us that we need to have a 30 amp breaker for this particular load. Don't forget to double check Rule 14104 Subrule 2. If you see the double squigglies inside table number 2, it means that that rule could take precedence over the size of overcurrent device that we choose. In this case, it's not a problem, and we're going to use a 30 amp breaker. Let's take a look at another example. Now we have a 1200 watt microwave rated at 120 volts, and it's also on a 75-degree rated termination temperature breaker. The first step, as before, is just to find the ampacity. We take our wattage, which is 1200 watts, divided by our voltage, which is 120 volts, and we get a 10 amp rated circuit. Now we have to determine whether or not this is continuous. The definition of continuous is, can I use it for more than 1 hour in a 2-hour period? The answer here is yes, therefore it is a continuous circuit. Next, we have to check their breaker rating. Is it rated for 100% or 80%? In this case, it's only rated for 80%. So we're going to increase the ampacity in order to accommodate that 80% rated breaker. So we take our 10 amps, divide it by 0.8, and we come up with 12.5 amps. This is the ampacity that I need to make sure I can maintain for my conductors, and this is the value I'm going to take to table 2. Are there any other heating considerations? In our case, no, they're not. Are there any voltage drop considerations? Not yet. We'll deal with that in a little while. Now we've answered all those questions, let's go to table 2. Since this circuit is rated for 75 degrees, we can use the 75-degree column. We follow it down and we find that a 14 gauge conductor will do the job, and that is rated at 20 amps. Normally we would go to table 13 and choose a breaker based on the ampacity of the wire. However, if you look at the table, it has a double squiggly right beside that 14, which means we actually have to go check on Rule 14104 Subrule 2. 14104 Subrule 2 states that I can have a maximum of a 15 amp breaker on a 14 gauge conductor, and I cannot exceed that except for under special circumstances. Taking a look at table number 2, we can see our double squiggly beside the 14, the 12, and the 10. If you look inside the notes, it says very clearly in the notes to check 14104 Subrule 2. 14104 Subrule 2 states that except as provided for by Subrule 1, the rating of overcurrent protection shall not exceed 15 amps for a 14 gauge copper conductor, 20 amps for a 12 gauge copper conductor, 30 amps for a 10 gauge copper conductor, as well as 15 amps for 12 aluminum and 25 for 10 aluminum. These are important because anytime that we come across a circuit that is going to require a 14, a 12, or 10 gauge conductor on a normal circuit, we need to make sure that we're using the 14104 Subrule 2 overcurrent sizing. The exceptions to this rule are things like motors, heaters, and capacitor banks, which have their own special rules when it comes to the code. There are a couple of other exceptions, and 26744 does give us 2 exceptions that we need to be aware of. First of all, wherever we have a freestanding range and it has a calculated ampacity of less than 50 amps, we automatically use the exact same receptacle and the exact same breaker on every single house. The reason for this is so that we can swap out the ranges without having to do any rewiring. So if someone has a very small range and they wish to upgrade, we've already accommodated that upgrade by installing a 14-50R receptacle and installing it on a 40 amp breaker according to Rule 26744. Let's look at a range example to see how this works out. We have a 14 kilowatt range with a 122 40 volt rating, which means it's dual voltage, which means it's on a 2-pole breaker, and it has a 75-degree termination temperature. The first step, is calculate the load. Instead of just taking the wattage and dividing it by the voltage like we did before, ranges have a special rule, and this rule is 8300. This rule has us treating ranges much the same way as we did when we sized them for a service. We still take them at a demand factor. 8300 tells us to apply 8000 watts for the first 12 kilowatts of load. We start with a higher wattage value with a branch circuit because the branch circuit is going to have more of a load on it when we compare it to the service. So remember, every time that you are sizing a range for a branch circuit, always start with a higher value of 8000 watts. The second step is to apply 40% to any amount over the 12 kilowatts. In our case, we have 2 kilowatts over. Therefore, if we take the 2000 watts, multiply it by 40%, we end up with 800 watts. We add the 8000 watts together with the 800 watts and we get a total calculated value of 8800 watts. This is the value that we're now going to divide by our voltage, and remember to use your highest voltage. 8800 watts divided by 240 volts is equal to 36.667 amps. Now that we know what the calculated ampacity is, we automatically follow Rule 26.744, and we don't have to worry about Table 2 or Table 13 or 14104. We automatically install a 1450R receptacle because we have a calculated demand of less than 50 amps, and we automatically put that on at least a 40 amp breaker. This is a typical range for any type of house. Based on Rule 14104 Subrule 1, we can choose our overcurrent device according to Rule 26.744, which is going to be 40 amp, and we have to accommodate a 50 amp receptacle. So when we choose a wire, we want to choose a wire that's going to at least handle the same ampacity of our receptacle. Therefore, Table 2 tells us to install a number 8 gauge wire rated at 50 amps. Another exception that we have is with heating devices. So anytime that we have electric heat inside a home, it does not follow the same rules. Take a look at 62.114 subrule number 7. This says that for services, for feeders, and for branch circuit conductors, supplying only the fixed resistance heating loads. So anytime that we have a branch circuit supplying a baseboard heater or an in-wall electric heater, we need to look at this rule. And it says it shall be permitted to have an ampacity less than the rating of the setting of the overcurrent protection, provided that the ampacity is not less than the load and at least 80% of the rating of the setting of the overcurrent protection. This means when we're sizing the conductors for a heating circuit, the conductors must at least take the full ampacity of the circuit itself, and it must be at least 80% of what the breaker size is. Subrule number 8 says that where the allowable ampacity of the conductor does not correspond to a standard overcurrent device rating, then we can use the next size up. But beware with that because we still need to maintain that 80% between the conductor and the overcurrent device. Let's look at this example of a 27.6 amp electric heater with 75-degree termination temperature. First step, of course, is to find the ampacity, which is given for us. The second step is going to go and find the wire immediately. So we can take this 27.6 amps directly to table number 2. We know what a termination temperature is, so we're going to look in the 75-degree column. Now we find a value that's equal to or larger than 27.6, and we end up with a number 10 gauge conductor rated at 35 amps. The 35 amp value now has to be within 80% of our overcurrent device. Now we go to table 13. Since my 35 amps must be within 125% of the conductor ampacity, we're going to do the calculation of 35 amps times 125%. We can also do 35 amps divided by 0.8 and it would be the same calculation, but we come up with a value of 43.75 amps. According to Rule 62.114 Subrule 8, we are allowed to bump this up to a 50 amp, but I'm going to warn you that's not always a good idea. If I can make this circuit run safely and consistently without any nuisance tripping on a 40 amp circuit, that would be a better choice. If I do run into trouble with nuisance tripping, I can upsize the breaker to a 50 amp circuit, but the inspector might also want me to upsize the wire to accommodate that. Since my wire must be at least 80% of my breaker rating, if we go with a 50 amp rated breaker, then I must go with at least a 40 amp rated wire, which bumps me up to a number 8 conductor. Let's look at another example where we're going to do a slightly smaller heater. This is a 20 amp heater rated at 75-degree termination temperature. The steps are all the same, so first we find our ampacity. Next, we take that ampacity over to table number 2, determine what our termination temperature is, and find the appropriate wire size. In this case, we have a 14 gauge conductor that is rated at 20 amps. Remember that I said earlier that heaters were an exception to the rule 14104, so we don't need to go looking at that rule. Instead, we're going to take our 20 amp rated wire, multiply it by 125% to get a value of 25 amps. Rule 62.114 sub-rule 8 will allow us to go up to 30 amp. However, a 25 amp breaker is not that uncommon to find. If we do choose to go up to a 30 amp breaker, we must still make sure that my wire is going to be within 80% of my overcurrent device. So I'm going to need to bump up my wire to a 12 gauge, which is rated at 25 amps, since 24 amps is 80% of my 30 amp overcurrent device. Make sure you're running through these examples a couple times to really understand how to size electric heaters. They are an exception to the rule compared to most of the other branch circuits that we have, so it's important that you understand how to do them. When it comes to my general use circuits and my lighting circuits, we don't necessarily know what the ampacity value of our load is going to be. So Rule 8304 states that for every device that we have on this circuit, we automatically size them each for 1 amp per device. That means that if my breaker is rated at 80% and if a 15 amp breaker, I can have a maximum of 12 devices on there. Keep in mind, this is only for current drawing devices such as lights and receptacles. This does not include any switching devices. 8304 states that depending on what the rating of my breaker is, will also change how many devices I can put on it. And I want you to remember, it's not always a good idea to fully load your circuits. If you can get away with putting fewer devices on a circuit, it allows you more flexibility to change things as you need to. Make sure you read through 8304 to see what the loading can be on each type of circuit. The loading for a 15 amp circuit compared to a 20 amp circuit will always depend on the rating of the breaker that it is attached to. Typically, we're going to be using 80% rated breakers, which are typical for housing. Therefore, we can have a maximum of 12 devices on a 15 amp circuit and a maximum of 16 devices on a 20 amp circuit. Another thing that we need to be aware of is that not everything is as simple as looking at it from a duplex receptacle. Although duplex receptacles are the most common type of receptacles we do have other options. Sub-rule number 2 addresses these options. If we use a duplex receptacle, it is considered to be one single outlet as per Rule 8304 sub-rule 1. If we're going to use a triplex receptacle, it means that we have 3 different spots to plug into. This is actually 1.5 outlets to be used in sub-rule 1. If we have a quadruplex receptacle, this is 2 full outlets according to sub-rule number 1. The last thing we need to look at is a voltage drop consideration. Voltage drop occurs whenever our wire is sufficiently long enough to actually impede the amount of voltage that gets to the end receptacle. Normally, we only worry about this on very long runs, but what we realized is that in some houses, from the time that you leave the panel to when you get to the end device, it can actually be quite a long run, especially in large 2-story homes. We're going to take a look at Table 68 to determine if and when we need to upsize our wire. Table 68 takes into account the voltage drop considerations of any wire up to a certain degree. If we're going to use a 14 gauge conductor, for example, we can put that on a 15 amp circuit as long as that circuit does not exceed 38 meters. If it does exceed 38 meters, we have to upsize the wire to number 12 gauge conductor, and now that is good up to 60 meters. If we exceed 60 meters, then we have to upsize it again to number 10 gauge conductor. If we go over the values that are within this chart, we can always look at chart D2 in order to determine what other voltage drop considerations need to be accounted for. This means that when we start to plan out how our circuit is going to be run inside the house, we need to think about the voltage drop considerations. So when we take into account the length of the wire from the panel through each device all the way to the last device, if that exceeds 38 meters, I can no longer use a 14 gauge conductor. I would have to upsize the entire circuit to a 12 gauge wire instead. This method is called daisy chaining and is very typical in most housing applications. But one option that we have to daisy chaining is to do a split circuit instead. A split circuit is where you find one point to take your circuit into multiple different directions. This won't save you any wire, but what it does is it will save you the length from the panel to the end device on each leg of your split. By doing this, we minimize the amount of wire that we are going to have in any one leg. Therefore, we avoid having to upsize our wire according to table 68. You've reached the end of this module. In the first video, we looked at what kind of requirements are required for a single dwelling panel board and how to select it and what you need to think about. In the second video, we looked at the branch circuits, how to size our wiring and overcurrent devices, as well as the other considerations to think about whenever we are planning any branch circuits. Make sure that you're going through the module to look at this information again and read through your code rules carefully. Go through the Blackboard test to make sure that you understand this knowledge. When you're ready, go on to 205D.